Introduction. And hi, everyone. I'm Shen, and I'm going to talk about this paper, State Machine Replication Among Strangers, Fast and Self-Sufficient. And this paper is going to appear at this year's Crypto, and it is a joint work with Juan Garay and Aglos Kayas. OK, so let me first explain the title a bit. When we say among strangers, we refer to the permissionless model. This is a setting which is very different from the traditional distributed computing, where the protocols are permissioned in the sense that the nodes are known in priori. However, in this permissionless model, nodes, they do not have the complete information on the set of the parties running this protocol. And more importantly, anyone can join and leave this protocol at will without notifying any other participants. OK, so the natural question is that, is there anything that you can do in this permissionless model? And we all know that Nakamoto created the Bitcoin blockchain, and thus the distributed transaction ledger in this permissionless setting. And it is also known as ledger consensus, or say a permissionless variant of state machine replication. And it has two defining properties, namely consistency and liveness, which at a very high level requires the honest transaction log to be a prefix of the other honest party, and the system can process all the valid incoming transactions in a timely manner. Oof, what happened? Well, I don't know why it's not aligned. Oof. Let me control it here. So is that OK? OK, so however, while these two properties are the most important two properties of ledger consensus, if we consider further improving this ledger consensus, then there are more interesting properties, which we consider in our paper. And I'm also going to introduce. There are three here: fast settlement, fast fairness, and self-timekeeping. I guess there's something wrong with my slides. So the first property is about transaction settlement time. And we all know in blockchains like Bitcoin, they follow this longest chain rule, which, in order for a transaction to be settled, then it has to be appended by sufficiently many blocks. And how many blocks are sufficient? In practice, people would consider 6 blocks are sufficient. However, in contrast, if we want to achieve cryptographic security, which means that the probability that a transaction gets reverted in the future is negligible, then transactions has to be appended by polylog kappa that many blocks, where kappa is a security parameter. So here, as you can see, Bitcoin is actually asymptotically slow. However, in contrast, in the permissioned setting, what happens is that there are some SMR protocols that can achieve the expected constant settlement time for all the transactions, which we call it fast settlement. And obviously, the first property that we want to achieve is fast settlement in the permissionless setting. And the second property is about fairness. So here we have a very interesting question. So that is, in the permissionless setting, if you don't have identities at the first place, then who should have access to this permissionless state machine? And the answer is quite straightforward, that in order to have access, you have to grant yourself access by inserting this special symbol. And in the context of Bitcoin, this is exactly what the Coinbase transaction does. So what it do is that it will found an address, and if you know the secret key, then you can later issue transactions. So with this in mind, we want to define fairness in this way. So whenever a Coinbase transaction is introduced, then an honest party should get selected with probability, which is roughly proportional to her computational power. However, we all know that Bitcoin is notoriously bad for achieving this notion of fairness for many reasons, like the network latency, they can create forks, and also the malicious parties, they can launch some very simple attacks which can discard honest blocks. And there are indeed some work which tries to achieve fairness for Bitcoin, but in our work, we consider one step further, which is called this fast fairness, which means that we also want to achieve fairness in expected constant time. And for both settlement and fairness, we will talk about this expected constant time. However, what is interesting here is that this timing thing is actually a very subtle concept in distributed computing. And I believe this part is not very well known, so I'm going to introduce a bit more about it. So here, what is a common strategy is that people would make some assumptions on the local clocks. They are either perfectly synchronized, as in the synchronous protocol, or they are completely useless, as in the asynchronous setting. But here, what we consider is this drifting clock model. So it's kind of like you can think of the hardware clock on your personal laptop. So they are drifting clocks in the sense that if they will deviate a bit after a certain period of the time. And if you do nothing, then they will deviate unboundedly from the real time. So the common practice is that you will use this network time protocol to synchronize the software clocks on your personal laptop, which at a high level, they just act like a trusted third party. However, we would not like this in our permissionless state machine replication, so we come up with this term self-sufficient. So this is to refer to SMR protocols that can be secure and do its own timekeeping under the only assumption that parties have access to their local drifting clocks. And if we look at Bitcoin, then what happens is that Bitcoin is not designed with this self-timekeeping things in the mind. So if you look at the code of the Bitcoin client, then what happens is that it just reads the system clock as the timestamp to prepare to mine the blocks. And if your system clock deviates too much from the clocks from the peer-to-peer network, then it will give you a warning to ask you to synchronize your computer. And which means that Bitcoin is obviously not self-sufficient. And there are some, so far we have introduced 3 new properties in state machine replication about fast settlement, fast fairness, and self-timekeeping. And there are indeed some prior works that tries to address these open problems. And I'm going to talk a little bit about them. So for this fast settlement, we have this Prism and Ledger Combiner paper that indeed achieves fast settlement, but only for non-conflicting transactions. Only for non-conflicting transactions, which means that if the transactions are conflicting, then the settlement time will degrade to super logarithmic again. If you think about like smart contract or say the Bitcoin script, then this might not be good. And the second property is about fast fairness. There is indeed a blockchain protocol called Fruit Chain that can achieve fairness, but again, in super logarithmic time. And for the self-timekeeping, I have to say it's quite unexplored, and we published the paper a few years ago at TCC, try to do permissionless clock synchronization. But the problem is that it's not in the most natural model, namely the drifting clock model, which I will talk about it like very soon. OK, so what we do here is that we come up with, there are 3 open problems in the design of permissionless proof-of-work-based protocols. And we come up with a permissionless SMR protocol that can achieve all 3 properties simultaneously, which is the main contribution of this paper, and I'm going to show you how this can be done. But before I proceed, I would like to first introduce a few basic modelings. So in our paper, we model the hash function to generate the proof of work as the random oracle. And our main building block is this protocol. So there is indeed a consensus protocol, a proof of work-based consensus protocol that can achieve agreement and validity. But in super logarithmic time, here polylog kappa that many times. And at a very high level, what this protocol do is that, by the way, here, when I say consensus, I mean Byzantine agreement, which is kind of like the one-shot problem. You have some inputs, and then you want to agree on a single output. So what's happening here is that this protocol will use blockchain to achieve agreement due to the common prefix property of blockchain. And then it can achieve validity by additionally ask parties to mine the input, in the sense that there are 2 mining procedures, one for the blockchain and another one for the input messages. And this dual mining procedure will give you agreement and validity at the same time, but the only problem is that it will terminate only after polylog kappa that many runs. OK, so what we do in our paper is that we improve this consensus protocol so that it terminates in expected constant time. And our SMR protocol is indeed by sequentially running this consensus protocol so that you can achieve faster settlement and fast fairness. To make this consensus protocol secure, then you need this 2-for-1 proof of work, which is used to kind of like combine the two mining procedures, but still they are independent. And the way that we do this is by using this parallel blockchain, which means that we will execute the previous consensus protocol in parallel for m parallel blockchains. And one chain is used to run one consensus instance. So here what we do is that we will use this M for one proof of work mining to bind the mining procedure of all the parallel instances. So it's kind of like we are running the same consensus protocol in parallel, but they are mutually independent. And the way that we do this is that we have the hash query output, which is kind of like kappa base, and we divide it into M chunks, and one part is for running one consensus instance. So this M for one proof of work will give us the fully independent parallel blockchains, which means that these instances are completely independent from each other. Okay, so let's see. When we have this parallel chance to run these consensus instances, what we know is that for a single instance, it has good properties, agreement, and validity, with overwhelming probability after super logarithmically many runs. And another thing is that it will have good probability with constant probability if you terminate in constantly many runs. If we only have a single chain, as on the left side, then this is not good because we would not be able to tell if we have this agreement of validity. But if we have parallel chains, then things get much better because we have this key observation. If you have good properties with probability beta, then if you have sufficiently many parallel chains, you will have good probability with beta fraction of the chains because they are mutually independent from each other, and the number of M is sufficiently large. So this is very good. This is very good, and I will show you how to use this parallel blockchain. And I want to say that we terminate in constant time, and we call this a phase. So what we do is that what we can do here. So with one phase, we already have validity. We already have validity because if beta is sufficiently large, then we can just account for the majority of the chance, the output of these consensus instances, and this will give us validity. The problem is for the agreement. Agreement, that's because for those chances that we do not have security guarantees, the adversary, he can just swing the output by, to say, give 0 to half of the parties, give 1 to another half of the honest parties. And the way that we solve this is by running these phases iteratively and use it to emulate a classical consensus protocol. And why this will work? That's because we have this chance, and some of them are good. The good chance we have, to say, common view on them, which will emulate like an honest party in classical consensus. And for the bad chance, we don't have agreement on them, and they will emulate kind of like the bad parties in the classical consensus protocol. Okay, so the consensus protocol, the classical one that we will run here is this king consensus. And this is a protocol that can terminate in expected constant time. The key thing here is that when parties, they are confused, they don't know which value to agree on, then they will run this last part. The oblivious leader election part, which will elect an honest leader with constant probability. And if this is the case, then you will terminate. However, classically, to run this oblivious leader election, what will happen is that you will need some very advanced secret sharing schemes, which requires some kind of interaction, which is not very doable in this proof of work setting. So what we come up with is that we replace this oblivious leader election with a very simple procedure, which we call it the king chain rule. So what happened here is that we will fix the first chain as the king chain. And what we do is that whenever parties are confused in the sense that they don't know which value to agree on, then they will simply replace their input with the output of this king chain. And that's it. That's it. It will just fulfill the same goal as this classical consensus protocol. And I will give you some very high-level intuition on how this will work. So what will happen here is that with parallel blockchains, the adversary's power is kind of like diluted, which means that in each phase, he is kind of like he's going to attack successfully on a very small fraction of the chance. However, the good thing is that he would not be able to select which chain he's going to succeed in attacking, which means that even if we fix the first chain deterministically as the source that we will refer to when we are confused, the adversary, he cannot, to say, attack the first chain permanently, which means that we will get good properties from the first chain with constant probability. And this immediately gives us the expected constant time consensus. So that's it. And if we sequentially run in this protocol, then it will give us state machine replication with faster settlement, but also with one more thing. So here, we get agreement and validity, and we run it sequentially to get SMR. But the problem is that the validity property in multi-value, the Byzantine agreement might be too weak. It is indeed too weak for achieve liveness, right? Because that's multi-value, the Byzantine agreement, so validity was too weak. And the trick that we solve this problem and achieve faster settlement is that what we do is that we add an additional layer of lottery on this king chain. So it's kind of like we slightly tweak the way that we decide the output on the first chain if we are confused. So what we do if we are confused and we want to replace our input with the output of the king chain, then what we do is that we have an additional layer of lottery, which means that honest parties will replace the input value with the input on the first chain with the minimum hash. So at a high level, what happens here is that with constant probability, the first chain is good, and everybody will refer to the same block. And again, with constant probability, the block that they refer to with the minimum hash will be a block that is generated by the honest parties. Yeah. And again, which means that with constant probability, they are going to agree on an honest input, and this gives us liveness. And that's it. We get state machine replication with faster settlement. So to make it truly permissionless, we need to do two more things, which we did in our paper. That is, the whole framework should be done in the variable difficulty setting. We did it. And also, additionally, because it is permissionless, the new parties, they would like to join the protocol, and they have to catch up with the other honest parties, which is kind of like tricky in the constant time. And we did actually design a bootstrapping algorithm that can let parties to catch up with others in constant time. So that's it. I'm not going to talk about the technical details, but this is a very high-level intuition on how this protocol works. And with this in mind, with this minimum proof of work output selection on the king chain in our mind, we immediately get faster fairness in this way. So it's kind of like we were just, for faster fairness, we want to select an honest coin-based transaction with probability proportional to the computational power. And if we add an additional phase before we execute each Shen-King consensus invocations, then we already get it, because in the sense that if parties keep mining their own coin-based transactions and submit them to the first chain, then we know that with constant probability, this first chain is a good chain where every party will just replace their coin-based transaction with the same output from this chain. And again, the minimum hash will give you constant probability that this coin-based transaction is indeed an honest coin-based transaction. And this gives us fast fairness. OK, so that's it. And the last property that we are looking at is this clock synchronization, the self-time keeping things. So for this property, we need to do clock synchronization. That's because, remember, we are in this drifting clock model. The local clocks, they will run at different speeds. And also, if you don't do anything, then they will deviate from each other. The honest parties will deviate from each other unboundedly, which means that you have to try to tighten the clock skews periodically. And as I said, we want to achieve two things. The first thing is that the skew among the honest parties, they should be bounded. And the clock value that parties output, they should be a meaningful clock value in the sense that it should not deviate too much from the real time. So the way that we do this is actually from our previous TCC paper. But it does not work for the drifting clock model, but we still use it as a sub-procedure that I'm going to talk a little bit about it. So this is very simple, actually. The consensus protocol that I said previously, it can also be used to do self-time keeping if we extend it a little bit in this way. So when you prepare the input for this consensus, what you do is that you also include your local time. And all the honest parties, what they do is that they will bookkeep to say kind of like the local receiving time of all the inputs. So, and this is already very good to run synchronization. So, 1 second. So what happens here is that what you do is that consider you only have a single chain, and you have some synchronization beacons. It's kind of like the inputs with timestamps. Now we call them beacons. The beacons recorded on the blockchain. And what you do is that for each beacon, you compare the difference from the timestamp recorded and its local arrival time. And you add the medium to your local clock, you get your new local clock. And if every honest party to do this computation locally, then it will give you a very tight, it will give honest parties very tight clock skews. But the problem is that this only works for loosely synchronized clocks, loosely synchronized local clocks, but does not work for the drifting clocks. Again, the reason is because how long to say? How long is the interval that we can do this kind of clock adjustment? In the single chain case, we have to do it for polylog kappa, that many rounds. But if we are in the drifting clock model, then the skew in superlogarithmically many time is already superlogarithmic, which is not good. No blockchain protocol, proof of work-based blockchain protocol can be proved secure with this amount of skew values. And it only works for what is called the imperfect clocks in these two papers. But it is not the natural clock model that we will consider about. So what we do in our paper is that, remember, in our paper, we want to do it in the drifting clock model. And the way that we do it is, again, using this parallel blockchain, which, at a very high level, parallel blockchain will give you like a set of new clock values, and a lot of them will be very close to each other. So now the problem is that how can you use this? How can you further tighten the honest local clocks if you are given these clock values? So here, as you can see, parallel blockchains will give you a set of clock values. And the way that the adversary he can attack these clock values is that he can either give you some very crazy clock values, which will let your local clock jump to some very crazy timestamps, very crazy time, or he can give honest parties different but very confusing clock values, which will kind of like try to further deviate the honest parties. And there are two challenges here. And the way that we solve these challenges is by running this approximate agreement. What we do is that with parallel blockchains, we can run this approximate agreement approach to do this clock synchronization. So the operations here are not that complicated that I'm going to talk about it. So with parallel blockchains and also the clock synchronization protocol on a single chain that I talked previously, you do it in parallel m times, and this gives you m different clock values locally. So what you do is that you first drop the largest and the smallest clock values to avoid you from going to those crazy times, and then you do this operation for the remaining clocks. You split them into different groups, and for each group you select a representative, and then you compute the average. This one seems a bit complicated, but we prove in our paper what will happen is that if you run the parallel blockchain and you do all these computations locally, all the honest parties do this computation locally, then you will have clock with bounded skews. Bounded skews, which is a kind of like a multiple of the network delay and the bound on the clock drift rate. So which solves the permissionless clock synchronization problem with drifting clocks. And the main takeaway of this paper is that, one second, there are three open problems. There are three open problems in the design of permissionless proof of work-based protocol for faster settlement, faster fairness, and self-sufficient timekeeping. And we come up with a protocol. We come up with a blockchain protocol that can achieve all three properties simultaneously. And there are some future directions of this paper. Namely, I just want to mention a few. So the first is that we only show the feasibility, but the parameters are not tight at all. It terminates in expected constant time, but the constant is a large constant. So it's possible. It might be worth to look at the concrete parameterizations of the protocol. And another one is for the faster fairness. For faster fairness, we kind of like use a very naive way of generating a very naive way of selecting coin-based transactions. So it's kind of like one transaction is selected for each consensus invocation. But obviously, you can do it, in a much better way, I believe. And also, it's also very interesting to see how self-healing in Bitcoin can also apply to this setting. And the last question is obviously if this framework has any implications on proof of stake with dynamic availability. Yeah, and that's it. That's my talk. Thanks. Ooh. Hey.
Okay, yes, we have time for one quick question.
Thank you. This was dense presentation, so apologies if I missed the point.
Mm-hmm.
But you said that in order to dilute the power of the adversary, you went from one chain to
Yes.
multiple parallel chains.
Yes.
But then I noticed that you say that we depend on the king chain to sort of help the other
Yeah.
parallel chains. So what happens if the adversary manipulates the king chain? How
Ah.
does it affect the other chains?
Yes, so the thing is that the adversary, he can attack the king chain, sure. And in that case, he will give different values to different honest parties. So, which means that they cannot agree, right? They cannot agree, so they will go for another iteration of this procedure, so that they will try to do try another round on the king chain. And the thing here is that the king chain will only fail with constant probability. So it's kind of like you will try it iteratively, and you wait for the lucky time that everybody agrees. That's how this expected constant time consensus protocol works at a very high level.
Okay, thank you.
Yeah.
Okay, maybe one more quick question.
Yeah.
Great stuff. Worked very hard on this problem. Couldn't solve it a few years ago. As you talk, I was trying to think, where did I get stuck? So I remember one difficulty was the following. So you are basically relying on each chain to be a participant
Yes.
in a BFT protocol.
Yes.
So the difference between a chain and a participant seems to be that, for example, when you vote,
Yeah.
the chain can actually revert it.
Yes.
So in a BFT protocol, however, when you vote, you can't change the vote anymore.
Yeah.
The vote is already sealed.
Yeah.
How do you overcome that issue?
That's how we do in the bootstrapping procedure. So it's kind of like if everybody is always online, then it's almost fine because you only look at the most recent phase that you are working on, and for the previous intervals, it can get reverted in the future. As you said, the chance can get reverted. That's fine. We don't care about it. So the way is that we design a traceback mechanism, which I didn't present in this talk. So the main thing is that if you obliviously agree on a phase on a single chain, then it's kind of like you can use a weak agreement style of things to keep voting, keep voting. So it's kind of like you will obliviously agree on a chain, and then in the next interval, all the honest parties will vote for kind of like the block on the tip for this interval. And if you do this continuously, it's kind of like you have this weak agreement on all the chains that you have common view. And then the joining parties, what the new parties come to this protocol that they can do is that they can starting from the tip of the blockchain and then trace back one by one. So they would not be able to know which subset of the chains that are indeed, parties agree on previously, but this agreement is kind of like achieved in a very oblivious way. And the security of the protocol only relies on the fact that parties have an oblivious agreement on a sufficiently many fraction of the chains. And that's it. Yeah. Thank you.
Okay, let's thank the speaker again.